Hi guys, well I'm back to make another video. Sorry it's been a while, but had some issues going on around here, and so anyway, we're back on making videos. We're going to continue with the lessons and stuff on the Admiral TV. Now it is effectively done and working, and still got a little tweaking to do with the picture. But the IF has been aligned and the tuner's been aligned and working good. Little issues with, getting it better centered and tweaking the linearity and stuff. But I'll wait until I get a lot closer getting it back in the cabinet before I do that. It seems like each time I lift this chassis and move it around, the little flexing goes on, and it kind of knocks off the centering a little bit sometimes and stuff, slightly, and you have to mess with it a little bit. So anyway, no further ado, there it is playing, and we'll bring sound up.
Something different. Peter Shoulders must have a very good job that he really likes, because he lives in Havertown, Pennsylvania, and your job is in...
It's in Manhattan.
Okay, I have taken the Acela train from Pennsylvania, from Philadelphia to New York on a number of occasions. Even on the Acela, it's still how long a commute?
If you're just going from the train station to
it's not doing bad. The pitch tube is a little bit slightly weaker on this set, although the longer I've been using it, playing it, it has been improving. Of course, it's daylight right now. Even though I got the blinds closed, you can see that they're still letting in quite a bit of light. So, and these TVs are were designed at the time for low lighting. Turn it down a little bit. We're just running through a digital converter box. It's over there. I can only pick up a couple channels around here with it, and one of them's being stubborn. I can't pick it up today. So this is the most local station. There are a couple frequencies on it. This is 33.1, which is, it's actually channel 3. If I go up, this is the other one of them. If you notice, it needs to be lifted a little bit. The bars are normal on this because it's not a widescreen TV. Here they just box it in. If you see a black bar along here, it may move, may not move. That's just the difference between frame rates of the camera and the TV. So anytime you watch any of these old TVs on videos on YouTube, you're going to see this. So, but otherwise, it actually is working pretty darn good. Nice thing about Admirals, they are pretty easy to work on. They're relatively simple circuitry in them, but very reliable. So, in any case, I thought I'd let you know that it is running and stuff, and everything. So now we'll just go from there and go over the schematic. We're going to go through the try to anyway. Go through several circuits to kind of finish out the comparison to radio, and do that. So I'm going to get set up for that. I'll be back in a second. Alright, we're going to talk about the IF and compare it to a radio and see the similarities, and then we'll talk about the differences. First of all, let's see what we got in here as far as the radio goes. So bear with me here, and I'll get her set up. Can zoom in. here's our IF section for the radio. We have our mixer oscillator tube here, and we get an IF frequency from the difference between the two, between the tune radio station frequency and the local oscillator. The difference between those two is our IF, in this case 455 kilocycles. IF transformer, simple tank circuit on primary and secondary, that is tuned to 455 kilocycles, and then that signal is fed into the grid of the IF amplifier tube, and it amplifies the signal, sends it out from the plate to a second IF transformer, again tuned just like the first one, and then that feeds to our detector to be detected and get the audio out of it. Well, let's look at the TV. Now come up here and we'll have to zoom out just a little bit and widescreen it. We'll zoom in and look at one individual circuit. Now right off the bat, one difference between the radio and the TV is basically the number of IF stages, how much amplification I'm doing. The radio had one IF tube. There's 3 IF tubes in this, so I got 3 stages of amplification in the TV. No big deal. There are radios that's got 3. There are some radios that's got 4. There are radios that have quite a few IF stages and quite a few IF cans and amplification, and at some point I will talk about those in a later video, but for this particular instance we're just comparing between and contrasting between radio and a TV. As far as the actual theory of operation, there's no difference. We had talked about the tuner in the last video, which is over this way. It has a local oscillator and a mixer tube, just like the radio does, and it takes the difference between those frequencies and feeds them down through the IF. Now, in the strictest sense of the theory, basically we filter it so that we only get the frequency that we want, run it through, we amplify it, filter it again just to make sure it stays where we want it on frequency, amplify again another filter, and then the final amplification, final filter, then we send it to the detector. Now video is AM on TVs, so it will actually use the same type of detection circuit. In other words, basically, in this case, a single diode. This diode here is our AGC, which we talked about in a previous video, and compared it to the ABC and found out that really they are the same thing. They do the same thing. Now let's contrast now the differences between the two. Right off the bat is the frequency. Now this one, in this particular TV, actually has 2 IF frequencies. They do that to help get the bandwidth. It's called stagger tuning. It's a real simplified version of stagger tuning. Older Admiral sets, which really is a relative term since this set was built in 1950. Older means just about a year or 2 prior to this. They had stagger tune where there was 5 or 6 different frequencies. But in any case, we have, now don't pay, make sure that's on there. This says 2.31, that's wrong. The decimal point is the wrong place. It's 23.1 megacycles is the first filtering that's going to go through. We amplify it, then we hit a 25.3, amplify it, then we hit 23.1 again to amplify that. Send that through to be amplified, then 25.3 for a final. So we have 2 different frequencies, whereas on the radio we have just the one single 455 kilocycle. The reason for this is we need that broad band that we're looking for. Comes up, humps a little bit, dips and humps again, comes back down. The difference between the bandwidth is roughly 3.5 megacycles is what we want. So that's why we are using two different frequencies through here. The other difference is the radio. If you actually look at an IF in a radio, the separation between the coils, the primary and secondary, is fairly large, which creates what they call loose coupling. So they're fairly loose coupled. The nice thing about that, what happens with loose coupling is, let me draw a little diagram here. Kind of zoom in here probably. Well, we'll see if I can. In loose coupling, you end up getting a response something like this. It peaks up very narrow across here. If you tighten the coupling, the tighter you start tightening it, it starts getting a little more broad band like this. If you use a tighter coupling and couple that with two or three different frequencies, then you start getting something like that, or similar to that. So you start getting wider and wider bandwidth by adjusting the coupling, and then if you add in the fact that maybe I can stagger tune it, have one IF can at one frequency, another one at a different frequency, but still close together, I can start widening it out. I'll get a little dip in the center because of the overlap difference, but we'll get the two peaks that we need, and we'll get the broad bandness. And that's what they're doing here. These cans here, these transformers are actually fairly tight. They're not overcoupled, meaning that they're not literally like a transformer, like a power transformer, audio transformer, where one coil is literally over top of the other one. Not in the strictest sense. They are somewhat looser coupled than that. They didn't want to. You can overcouple an IF transformer. You get so tight, but the problem is you start getting a really broad band out of it, but then you don't get you lose something. You start losing gain. So they made a compromise between the coupling, how tight they coupled them, and how much gain they wanted to get. So, and by using a couple different frequencies, that allowed them to do that. There are some sets that uses overcoupling, and that's all they use. If they really want to get a pretty strong signal through it, they're going to have quite a bit of gain on each tube. But in theory, these work the same as a radio. It's the same principle. Basically, all the IF cans are doing, all the IF section is doing, is giving us one basic frequency, one band pass that I can amplify and amplify and amplify, and not have to worry about trying to retune it each time I amplify or lose something, and get, a good signal strength, get good selectivity through, and to get to my detector. So I have a good strong signal there that then I can amplify and feed out. In this case, with the TV, it's a video, and I feed that out to the picture tube. So I have good strong video to the picture tube. In a radio, it's audio, so you can get good sound out of the audio output tube. Now, what other differences are here? Well, that, if you haven't noticed, you will. But let's look back at the radio. Scoot this over here, and let me zoom in on the IF. The difference, the one thing I want you to look at is these IF cans. Okay, I got the primary and secondary, but there's a capacitor across each side. In this case, this radio is old enough that they, for tuning the IF, they used variable capacitors, padders, little screws on top of the cans that you adjust to when you do alignment. Newer radios, the capacitors were fixed, and they used cores in the coils that you would actually stick a plastic tool in and adjust those up and down, so that the core would either go in or out, engaging the coil. That would do your adjustment. But in any case, it's a capacitor in parallel with a coil. Now we come back up to the TV, and this is perfect right here. Okay. I have the coils. Where's capacitors? No capacitors here. Now, this uses, just like the newer radios, it uses a slug inside that for just an IF, just like newer radios in the 50s and so forth and on will do the same thing. But so that's not a big deal. But the big deal is there's no capacitors in parallel with this coil or this one. There's a resistor, but that ain't going to do any good for a tank circuit. So where is the capacitance? I mean, it's got to, in order for it to filter and stuff, we need something there to create some sort of resonant circuit. So what happened to the capacitance? The hint, more or less, well, the hint basically is in the frequency. And in this case, on this one, 25.3 megacycles, whereas on the radio it's 455 kilocycles. Okay, so quite a bit of difference in frequency, and that's where the hint is. It's in the frequency. When you get up in the upper frequencies in these ranges, then what they call circuit capacitance starts really showing its head. It really comes in view. Circuit capacitance is everything else in the circuit, including the capacitance between the windings of the coils and between coil, primary and secondary coil even. All these have capacitance. The wires, how they run, they run along the chassis, they make a capacitor between them and the chassis. The interelectrode capacitances inside the tube. Any decoupling capacitors that you may have, like this one here, all goes into the circuit capacitance. And it's all really basically in parallel with that coil. And when you're working with low frequencies like 455 kilocycles, as an engineer, it's in the back of your head. You know that circuit capacitance there, so when you actually do the design, do all the math out and everything, you want to add it in. You want to know it's there and add it in. But it doesn't make a huge difference. We're talking very small capacitances here. But when you start getting in higher frequencies, that small capacitance really starts affecting things. So they actually make use of that. The primary one that they're making use, say, on the secondary is actually the interelectrode capacitance between the grid and the cathode. But everything else in this circuit path in here is also taken into account for and figured in. This 1500 picofarad decoupling cap was actually picked for that size. For that, they needed it, they knew they needed it, but it was picked in, as far as the value capacitance, to fit into the circuit with this coil at that frequency, with the knowledge of all the other capacitance in the circuit. So the capacitor that is across here that you don't see is all the circuit capacitance, including what's going on inside the tube. All makes a parallel circuit capacitance for that coil. Same way over here. In this case, it's going to be the plate and cathode, and plate and grid and of the tube, the screen grid. All comes in account along with this decoupler here. And again, even the capacitance between the two coils You know, you got two conductors separated by insulation. That is a capacitor. So it's there, you just don't see it. If you looked at an engineering drawing, pure engineering drawing, you would actually see it. It would be there because it's drawn on there. And a lot of those engineering drawings are actually just expert, you know, just a little small section. They may just make one drawing just of this second IF amp circuit and another one for this one. So the circuits work the same, and they are the same, so don't let these be magical to you or be scary. They are working on the same principles. They are filtering out and band passing or passing through just certain frequencies to be amplified. Same way with the IF that's in the radio. That's all it's doing. Now from that point it moves on. I'll kind of scoot over here a little bit, probably widen the angle out, and we'll try to bring in better view here. Let's move this over a little bit. Okay. Now, once we go through the last IF, where do we go? Well, we go to detector. Now, since video, in this case, although they're going through this is intercarrier sound as well. There's sound signal going through here as well as video. Some TVs were built where they separated the sound off early on, just right after the tuner. So you had a video IF and a full-fledged sound IF as two separate entities. But in this case, we have just a single going through all this until we get to this point right here. This point here is the sound pickoff. It'll go up here and we'll back up, and we'll get to that here in a minute. But this detector, since sound is FM, it just goes round through. It doesn't care. It's amplitude modulation, or AM, that the video is, and that's what this detector's for. And it's just the dual diodes here. Well, actually the detector part's just the first diode up here, this top one. It's no different than radio. Same thing. We just got a single diode doing the work. Radios use a lot of dual diode, triode type tubes, like 6Q7, 6SQ7s, newer radios, 6AV6s and stuff. But in any case, they still have just the diodes in there. Sometimes they only use just one diode. They may tie the two diodes together, or they may as parallel on them, or they may take one diode and just ground it out and just make use of one diode. In the particular radio that we've been looking at, it actually only uses one diode, and it grounds out the rest, the other diode. So we'll zoom in on that. Give me a second here. There we go. Sorry about that. A little jumpy. There we go. Alright. So we're coming out of the IF. We only feed into one diode here. This other diode, if you follow it, it goes back to ground, back to cathode. Just hold on a second. I'm back. Sorry about that. Had a phone call. I think I left off with that second diode here coming down, coming across, and it's just hooked to the cathode. This all goes to ground. So it's just grounded out. They're using a single diode. Now on the TV, they're actually only using a single diode too for detection. So it's literally not any different. Widen this back out so we can see it. Rotate this a little bit. Now, so it's just using the same technique, just a single diode here, and then feeds on out to the video amplifier. In a radio, in this case, it'd be the audio amplifier. We already went over this line here, the AGC, and compared it to the AVC, which basically automatic volume control in a radio is nothing more than an automatic gain control, because that's all it's doing. And we already talked about that. That comes off the second diode, and it picks a signal off that it needs through this 120 picofarad cap. So this works no different, you know, because it's an AM signal on the video, so it's basically what you're doing is you're taking half that signal. That's what detection means. Then you'll feed it through some filtering, just like you do in the radio. You got to filter it some to get rid of the IF, and so you're left with pure video in this case, or in radio, pure audio. Now let's look at one of the other circuits. Now one other thing I want to talk about, or not really talk about, but I will go through, I've said this on the previous video, every circuit in more detail in this series, but it'll be down the road in the series, so we can go over more depth in the theory. So don't worry about that if you got some questions, or you're like, gee, you know, I wish you'd went over this a little more or something. We will go over it a lot more in depth. Right now it's just a simple comparison to radio. So now we're going to move up, and let's look at this audio thing. Bring it back out just a little bit and see if I can get this all on the screen. Yeah. So like I said, after the detection, we pick off audio here. Well, that goes up through this line, comes across here, our audio signal, and really right now is also some video in it until we get to the 6.8 picofarad cap right here. That cap blocks out the video signal, allows the audio to get through. Now let me kind of get us a little more in touch here. And there we go. So now, from this point on, we've got a couple IFs and an IF amplifier, but this is nothing but more, it's just an FM radio now. At this point, this sound is like any other FM radio that you don't run into. The only difference between it, really, is its IF frequency. In TVs, it's going to be 4.5 megacycles as a general rule for the IF. On radios, FM radios, especially late 40s on, it's 10.7 megacycles. That's it. We got a IF here, tuned coil, feeding into sound IF amp, and then more of a standard transformer. This is the IF side. This side here, along with the secondary coil here, and the 6AL5, this is your ratio detector. It's similar to discriminator. There's two different types, but they basically do the same thing. This detects FM signal, gets the audio out and feeds it out, and we'll feed it down through here, through point C, and through our coupling cap to the high side of the volume control, just like on a radio. Again, another coupling cap, and feeding into a 6AV6. In this case, these two diodes are grounded because we don't need them. We're just looking for the triode, is all we're looking for. Now, let's see if I can pull that over. I don't know if on this screen I can. Yeah. Okay. And right over to the edge, then that feeds to a 6V6. Just same type of tube you find in any radio. Audio tube, which then feeds in. You can see the primary here of the audio transformer and output transformer, and feeds to the speaker. No different than any radio that you'd run into. This audio section should be very familiar with any audio section of any radio. You'll have some sort of first triode. In the case of radio, generally this is also acting as your detector, because it's usually just like a 6AV6, it's a dual diode triode. By the way, 6AV6 is really the newer version, or the miniature version, of a 6SQ7. were the 6SQ7 and its older brother, or older self, of the 6Q7. Both were octal tubes. This is a miniature 7-pin. Basically same characteristics. It really was designed basically as a miniature replacement for that tube, and this became the popular tube to use in radios for dual diode and triode. So, but in a radio we'd use these diodes here as part of our detector, and then we'd feed the signal in through the volume control into the grid, and to get a first audio amplification, feed that out to say a 6V6 or 6F6, 6L6 or whatever. That pretty much takes care of that part. Now again, I will go over everything on this in a lot more detail, but this was just more of a comparison thing. The one last circuit that we can compare is the power supply. Now, right off the bat, the first thing I want you to realize on the power supply on this radio, or this TV, excuse me, is the fact that this is a combo set. That's what this big plug is. So the power supply, it has one single power supply here. That has to not only supply voltages for the TV, but it also has to supply voltages for the radio section. Now the radio section in this particular unit combo is only just the mixer, oscillator tube, IF, and detector and first audio. That's all it's on that in that circuit, because the output goes then feeds to the same audio output tube. That 6V6 will feed from the radio if you're using the radio, and then out to the speaker, because we use the same speaker. Otherwise, that's why you get all this extra, these 3 extra resistors in here and everything, is to feed voltages through these lines to the plug and out. The rest of it, really from here up, is just like any other, are very similar to most TVs. Now some TVs may not have as many different voltages, some may only have 1 or 2. This one actually has 3. This one actually goes to the lower voltage stuff, such as the sync circuits, sync separator and stuff, as well as to the IF, and I believe also the tuner. This is going in and feeding some of the horizontal. This actually feeds the output tube. The output tube, that audio output tube, likes having a lot of voltage to it, as it does in a radio. As far as the transformer and power supply, or the main point here, this section here with the filters, first pi filter, it's no different than any other radio. You know, that's transformed. You have a transformer, you have primary, and you'll have, you know, if it's older, with using a 5-volt rectifier tube, then you'll have a 5-volt filament, 6.3-volt filament, and then your high tension or high voltage secondary for the plate, for the B+. So it's literally, and if we scoot down here and look, basically the same thing. This one's kind of a little different, drawn a little differently, because over here on this side on the drawing is where the 6.3 is, but here's your high tension, high voltage, and then here's your 5-volt for the tube. Use a 5X4 in this case, where TV's using a 5E4 only because the TV requires more current. And then we feed that through to one capacitor filter cap right here, through this plug to the speaker, the field coil to make up a tank circuit. This is between the 2 filter caps, so it'll come through that, back through into the next filter cap. So on the TV, it's very similar. Now we actually have a double pi filter circuit here. The first one is right here, where we're using a resistor, and there's radios that also use resistors as well as the pi filter. But we have a cap, resistor, cap. But here's the focus coil. We also use it in the power supply. From this cap we feed down, we go through this coil to another filter cap here. So this makes up another pi here for even more for the 210 volt and the 120 volt circuits. They're better filtered. The audio circuit's only just getting the filtering of this, which is the 238 volts. But otherwise it's no different than anything else. So there is something I want to talk about on this, and I'll get to it in a second here. Give me a second. Alright, I'm back. Sorry about, well, to you, I wasn't really gone that long. What I had to do is plug in find my cord adapter and plug in the camera. It was about to go dead. Alright, the thing I want to talk about, I was asked about and asked if I'd go over by one of my viewers, is dealing with this filament right here. Okay, because if you follow this lead through, we got 238 volts there on that. Oh, sorry about that. I guess I ought to rotate so you can see the 238 volts. There we go. You follow from this point, like pin 8 here, all the way across here, it says there's 238 volts. Now, that's a 5U4, and you know, you can have 5Y3s, you can have 5X4s, whatever. The whole idea of the 5 means it's a 5 volt filament. So tell me, how in the world can I have 238 volts there that's on this lead, that's hooked to pin 8, that's hooked to a 5 volt filament? Why? How can I have 238 volts on 5 volts filament? I mean, it should burn it right out, right? Well, first of all, let's pick a nice round number, 240 volts, because we're dropping some voltage through here. I don't know for sure how much. I'd have to figure out all the current that's going through this 50 ohm resistor to know exactly what the voltage is here. It's going to be more than 240, but to pick nice round numbers, we'll pick 240 volts is right here, or in other words, right on pin 8. Now, that 240 volts is on pin 8, it's through here, it's also on pin 2, it's also through this winding, and it's back. Well, it just makes a nice little loop. Does nothing. There's no path, there's no nothing for it. It's just going around in circles. Okay? The only place that 240 volts can do is go out this way. But I need 5 volts for this. Well, that 5 volts is being generated right here. What really is going on is, at this point here, there's 240 volts, just say, for sake of argument, round numbers, 240, but on pin 2 to ground would be 245. The difference between pin 2 and 8 is 5 volts. In other words, this 5 volts that's needed for this filament is above this voltage here, the 240 here, which is actually more now. Like I said, this resistor drops more, but I'm picking around numbers. So if I'm saying there's 240 volts before it goes to that resistor, then this is 5 volts above the 240. It's all relative though. The thing you need to remember is how I can have that voltage there and not hurt this filament is the fact this does not connect to ground. It's isolated. There is no ground connection. None of this little loop from pin 2 through the winding back around to pin 8 ever goes to ground. Even if you say, well, wait a minute, it goes to ground here. That's a filter cap. Capacitors block DC. We're talking DC here for the most part. You know, this 5 volts is actually just a ripple on top of that 238. But that blocks the 238 or 240 volts. So there's no ground path there. You can take it on out and follow it out through the circuitry. Well, where's the 238 going? It's going to plates. There's no actual physical connection inside a tube, unless it's shorted, No physical connection inside a tube that connects the plate to ground. Now there's a flow of electricity and everything, makes a complete circuit that eventually goes back through ground. But there's no actual physical connection. So this winding, this filament and winding are floating. And they float above whatever voltage may be here. 240, we've just been picking round numbers, is there. Where's that 240 come from? Well, that's coming from this winding here. We get a full wave rectification because we got this grounded here. Now this does go to ground. But at one particular half cycle in the AC, if we pick an instant at a time, one half cycle, this is going to be plus up here. This will be negative here. This side will not conduct. But since this is plus, we get a conduction path of voltage. We'll get 240 volts here through that conduction path. That will go through all the circuitry, come back around to this ground point and back in. So that's how you get your circuit going through. If nothing else, you can, if you want to see it, you can take it this way. Follows through, comes down, goes through here. That's ground, just the same as this. So comes back. We got a completed circuit. The other half cycle, we got a plus down here and a minus up here. So now it goes through this plate. Again, still just 240 volts or whatever it is. It'll be above that, but so across both those, though, if you measured from here and here, would be double that voltage. But since we center tap to ground, we're only actually making use half at any one point in time. But this ground and this winding does not hook to this. The only thing they share is mutual inductance. That's it. So you can think of this as an isolation transformer, because it's all power transformer really is. It's an isolation transformer. I isolate this primary from all these secondaries because there's no connection. Zero connection. In fact, all an isolation transformer, the very basic basis and the most basic isolation transformer, simple one-to-one transformer, has a primary with a certain number of turns and a secondary with the same number of turns. They don't have no connection other than mutual inductance, and that's it. But there's no physical connection. So any power transformer is the same thing. That is built this way. Now there are auto transformers and those are different. But where you've got an actual separate winding for your primary, separate winding for your high voltage, separate winding for your 6.3 down here, and separate winding for your 5 volt if you need it. They are isolated. And the fact that this does not connect to any ground anywhere, and in fact it is fully, completely isolated basically from all the other windings, all the other circuitry, is how it keeps from burning out the filament or damaging that winding. Even though there's high voltage here, this is 5 volts above the high voltage. So then when you actually look at it, the difference between pin 2 and pin 8, in other words, across that filament, is just the 5 volts. And that's it. So I hope that kind of explains that, so you kind of understand that. I'm going to go into this stuff a little more in depth in probably maybe the next video, maybe, or a video after that, because we're going to talk about how voltages are truly relative. I mean, you're taking voltage reading from a point to a point. It's a relative points, you know. And, you know, this 238 is relative to something. Well, it's relative to ground. So I connect a lead here and I connect a lead here. But they're also known as a potential difference. And actually that's what voltage is a potential difference. There's a potential difference of 238 volts between this point and this point. And we'll talk more in depth on that. And that has to do and how this can actually work just fine the way it is. So I think that's about it on this video. The next video for sure in this series, we will be away from radio. This pretty well finalizes any connections to radio. In the next video, we're going to start talking about our sync circuits, our vertical and horizontal oscillator circuits, and so forth. We'll start off with the oscillators. We'll talk about vertical and horizontal and how they develop in a signal, an oscillation, and so you can have a raster with no signal coming in. And then we'll go from there and go into our sync signals and how those sync signals actually interact with those oscillators, and so that we can get our video in sync and stuff. So next several videos we'll be dealing with, it'll take 2 or 3 videos to go through those circuits in depth. So and there's several different ways of doing it and stuff. We'll be talking about our high voltage, horizontal high voltage. In this particular TV uses a flyback, or also known as better term as kickback. Was actually the original term for it, but there's other ways of doing it. There's actually 4 real basic ways of producing high voltage for the anode, second anode or whatever, to pull the electron beam to the screen. So we'll go over those different ways and talk about them too. So until next time, thanks for watching. I want to thank my new subscribers and stuff, and thank you for your comments in advance, and a lot of you are quite kind with your words and stuff. If you have any questions, post them. Again, I will be going through everything and a lot more in depth, and when we start doing that, we'll start with the tuner. We'll go through its theory of operation, how it works and everything, and then into the IF more in depth, and the sound, the video, and of course, since the next couple 3 or 4 videos will be in the sync and oscillator circuits, we probably will not cover it because they will be in depth. So it'll take several videos to go through them really properly and do them justice. So again, thanks for watching, and sorry about it being really long. I'm trying to improve on time and trying to improve on the video and stuff, so hopefully we'll eventually get there. So I'll see you guys on the next video. Thanks again.